All right. Yeah, we're recording. So nobody has homework questions. 11.2. Don't worry about 11.3, 11.4 yet, because we haven't finished them. Okay, that's fine. Might be something everybody has a question on. So we started dot product last time. We're going to finish up our dot product section, also do our cross product section. And Kirby, you just going to ask me after class?
Or during break.
Okay. All right.
No
So that 11.2 homework is due tonight. It was pretty much the same as 11.1, except we threw a third variable, a third component. Probably asked a bunch of stuff about magnitude and adding, subtracting, maybe an application problem or two, vector applications, putting things in component form. It might have also talked about parallel vectors and collinear points. That's about what we did in 11.2. We just add that third component to it so we could have three-dimensional vectors. So in 11.3, we're going to talk about one of the ways to multiply vectors together, and that's with the dot product. And this is also called the scalar product, we said, because the answer is a scalar. And we just started going through the formula. That's all we got to class last time. We said to do dot product between two vectors, we multiply corresponding components, and then we add those results. So that we can do this for two-dimensional vectors, and we can do it for three-dimensional vectors. So for the two-dimensional vectors, we just won't have the v3 times w3 there at the end. It would just stop at component 2. But what we did not talk about is why we would need to know dot product and what it's used for. So most of the rest of this section is about dot product, what we need to use it for, some different formulas that use dot product, things like that. So I'm going to have just our basic formula again because we're going to be using it in every single one of these problems here. So if we have vector v with components v1, v2, v3, and vector w with components w1, w2, w3, we said the way that we're going to do dot product between v and w, and the symbol is literally just a dot. We multiply corresponding components, so v1 times w1, both of those are x components, so we can multiply them together. And then v2 times w2, v3 times w3, and then we add the three products together. And this answer is no longer a vector. Even though two vectors went into the calculation, what comes out is a scalar. Does anybody remember what we said about changing the order? Still get the exact same thing. It's commutative, right? Since the formula for dot product just has multiplication and addition are commutative. So the only thing that's going to look different is the W's are going to be written before the V's, but that product comes out exactly the same. So w dot v is exactly the same as v dot w. The order that those two are written in does not matter. And we showed that with an example last time. We worked it both ways and showed that we got the same answer both ways. So almost everything we do here in 11.3 is going to involve the dot product in some way. And we're not just going to be randomly calculating the dot product, we're actually going to be using it to do something. But just to make sure we all remember how to do it, if we've got vector v is -4, 1, 2, and vector w is 0, 5, -3, we are going to find v dot w. So remember, the components for a vector describe the change along each of our axes. So vector v, as we move along vector v from the initial point to the terminal point, the x value is going to go down by 4, the y value is going to go up by 1, the z value is going to go up by 2. So we think of those numbers as how the coordinates change from the initial point to the terminal point on the vector. And if it's in standard position, which means the initial point's at the origin, this also can represent the endpoint for the vector, or the terminal point. So for v dot w, we've got 3 multiplications to do. We've got to do -4 times 0. Both of those are x components. We've got to do 1 times 5. And we've got to do 2 times -3. And then add these results. So we get 0 plus 5 plus -6, which is -1. So the answer is just a scalar. It doesn't have any direction associated with it. It's not written with the pointy braces. It's not written with IJK. It's just a number. So that's why they call dot product a scalar product as well. So some of the properties for dot product, and these are just some algebraic properties that allow us to move things around, and we've already talked about it being commutative. Well, so we're going to see some different vectors in these properties. We're going to let u, v, and w be vectors. And let c be a scalar. So the first one we already know is that u dot v is exactly the same as v dot u. And we showed that with an example last time. And we know why, because it's just going to change the order of the multiplication, which is not going to give us a different answer. So that's the commutative property that says we can change the order and it would still be the same. So we did already talk about that one. Dot products also have a distributive property though. So if we wanted to calculate u dotted with v plus w, we could distribute that and do those two dot products separately and think of this as u dot v plus u dot w. So it's also distributive. And that not only works for addition, but subtraction as well. Property number 3 says we're going to take a dot product, u dot v, and then we're going to multiply it by a scalar. So even though we're dealing with two different types of multiplication here, one of them is a vector multiplication and the other one is a scalar multiplication, since our dot product only involves multiplication and addition, and then we're talking about doing another multiplication, all of this stuff can get moved around as well. It really doesn't matter what order we do it in. So right now, the way that we have the parentheses written, u dot v is going to be done first, and then once we get that answer, we'll multiply it by a scalar. But in actuality, we could multiply the scalar into u and then dot it with v, or we could multiply that scalar into v and then dot it with u. All of this is just multiplication. Even though it's two different types of multiplication, it's all multiplication. So it's associative and it's commutative because the c actually moved from the front to just the v. You don't distribute that. You only distribute across addition and subtraction. So if you think about just back from basic arithmetic, if I asked you to do 2 times 5 times 3, you wouldn't distribute the 2 to the 5 and the 3. Distributive is only for addition and subtraction. You would do 5 times 3 is 15, and then 2 times 15 is 30. And it really doesn't matter if we do 5 times 3 first, or if we do 2 times 5 first, or if we do 2 times 3 first, we'd get the same thing. So the same thing's true with vectors. But just be careful with the distributive property because it kind of looks like distributive property where you would give it to both of them, but that's all multiplication. Even though it's different types of multiplication, it's all multiplication. So it's just associative. There is a zero vector, and if you dot the zero vector with any other vector, you'll always get 0. So the zero vector, it depends what dimensions we're working with. It's just the vector that has all 0 components. So if we actually wrote out what the dot product looked like, we'd be doing 0 times v1 plus 0 times v2 plus 0 times v3. All those products would multiply to be 0, and then adding the 3 zeros would still get you 0. So dot product with the 0 vector is always going to be 0, just like multiplication with real numbers by 0 is always 0. And if you dot a vector with itself, so if you dot a vector with itself, you're going to get v1 times v1 plus v2 times v2 plus v3 times v3. Since all those components match, we really could write this as v1 squared plus v2 squared plus v3 squared, which almost looks like another formula that we have. It's just missing one part of it. Magnitude formula, right. Our magnitude does v1 squared plus v2 squared plus v3 squared. The only thing different is magnitude has a square root around it. So since this doesn't have a square root around it, any vector dotted with itself will give you the square of the magnitude. And that square just cancels off the square root that we're used to seeing on the magnitude formula. So any vector dotted with itself is just going to give you the magnitude squared. These aren't really anything that you need to memorize. They follow along pretty much exactly the same as what we would do with normal numbers. The last one, you don't even need to really memorize that. If you were ever asked to do v dot v, it's just as much work to write out the dot product as it would be to write out the magnitude formula. So we wouldn't have any test questions about any of these, but just knowing how to deal with them and knowing that we deal with dot product exactly the same way that we deal with products with real numbers. Now that's going to be different when we get to cross product. Cross product does not follow a lot of these properties. Cross product is very different. So we're just going to do a bunch of calculations just to demonstrate some of those properties and see what happens when we're asked to do different things with them. If we've got U is -132, V is 205, and W is 1/2 4 -1. We're going to find U dot W, and you guys can go ahead and start these because they're going to be really easy. We're also going to do U dot W times V. For W dotted with V. V dot V and magnitude of V. So we've got 3 vectors and we just want to do all those calculations. Now some of them are going to come out to be scalars and some of them are going to come out to be vectors. Actually, just one of them will come out to be a vector. Which one of those answers is going to be a vector? Any idea? 5 is just magnitude. 5 is just magnitude, so it's going to be a scalar. Number 2 is going to be a vector because when we do U dot W, we're going to get a scalar. So this is going to, on the second step, it's going to end up saying a scalar times vector V. And when we do a scalar multiple, we just distribute the scalar into each of the components. So in number 2, we're going to end up with a scalar multiple of vector V. And U dot W would tell us what scalar to multiply through by. So 2 ends up as a vector. All the other ones are going to end up as scalars. So number 1, just a basic dot product. What are we going to do to calculate U dot W? Tell me your products in your addition. -1 times 1/2, because that will be my X components for U and W. Multiply them together. And then 3 times 4, 2 times -1. So we've got 3 multiplications to do, and then we'll add the results. You end up with -1/2 plus 12 minus 2, which is 9.5. I don't care how you write that. You could say 9.5, 9.5, or 19 halves. Any of them are fine with me. Most likely, though, in your homework, it would want it as 19 halves. Usually they don't want you messing with decimals or mixed numbers. Decimals are okay as long as they terminate, but that's not guaranteed every time, and they don't want you to end up rounding a decimal that's a non-terminating decimal. So the easiest way to write all of them in a matching format that all of them will work is that irrational fraction. So u dot w is 19 halves. So this piece right here, I know is 19 halves. So really number 2 is just asking us to do a scalar multiple, do 19 halves times v. And the way that we do a scalar multiple is we just distribute the 19 halves to each piece. So in number 2, I kept it exactly in the order that it gave me, but we could have really done u dotted with v dot w. Those dot products, they're associative and they're commutative, so we could have done those 3 vectors in any order, and we should have gotten the same thing. So 4w dotted with v. The way that it's written right now, what should you do with the 4? Just distribute it to the w. But what we saw up here in our properties is we can really do anything we want with it as long as it gets incorporated into the final product. So if you want to, you can do w dot v first and then multiply your answer by 4. That way you don't have to write out a completely new vector. It's completely up to you. So we could do 4w first. We could do w dot v first. Doesn't matter. We could even distribute the 4 into the v and then do the dot product if we wanted to. So whichever way seems easier to you, like it makes more sense or it's less work. I really don't want to have to write out a new vector of 4w. So I'm going to do 4 times whatever w dot v is. And we haven't done w dot v yet. What do we get for w dot v? 2 times a half is 1. 4 times 0 is 0. And negative 5. Or minus 5. So w dot v is negative 4. And we're being asked to multiply it by 4. No matter what order we do that in, we should get negative 16. V dot v, we're just going to multiply each of the components by themselves and then add them together. So we get 2 times 2, 0 times 0, 5 times 5. V dot v is just 29. But if we were asked to do the magnitude of V, what would be different about our answer between number 4 and number 5? Number 5 is going to have a square root around it, right? The magnitude formula says do the square root of each of those things squared. So that's why we said V dot V gives you magnitude squared. Because if you square the magnitude, it's going to cancel the square root off, which is exactly what we have in 4. Same exact number, but without the square root. So just some different algebraic things we can do with dot product. Questions about how we got any of those or how we did any of them? Kirby, you double checking something?
Yeah, I somehow I got 98 for the 4W times V.
Did you do 4W first?
Yeah.
Okay. So if we do 4W,
4 times 1 half,
you should get, 2, 16,
negative 4.
-4. And then if we dot that with V, we're going to get 2 times 2 is 4. 0 times 16 is 0. Oh, you probably did something with the 16 to get such a big answer.
Yeah, I added them all.
And then 5 times -4 is -20. So your way, the dot product would have been 4 plus 0 minus 20, which is still -16. All right, so enough with random calculations. Pretty much the rest of this section is just going to be different formulas and different applications that we use dot product for. Some different things we can do with it, besides just calculate some random scalar associated with the two vectors. So the first thing, and probably one of the easiest ones, and pretty relevant as well when we have our vectors in standard position, is finding the angle between vectors. This is easier to visualize in 2 dimensions because when we draw our vectors in standard position, they look more like angles. It's easier to see the angles. It's a little bit harder to see in 3 dimensions. But if we have vector V in standard position, and then we have vector W in standard position, the dot product is going to help us calculate the angle between those 2 vectors. So V all by itself has a direction angle. W all by itself has a direction angle. But the angle between them would be the difference between those 2 angles. And there's a way we could just do this with trigonometry. It would be a multi-step process of finding V's angle and then finding W's angle and then comparing them. But with the dot product, there is a nice simple formula that says cosine of theta is U dot, let me do W. Cosine of theta is V dot W divided by the magnitude of V and the magnitude of W. This fraction will give us the cosine of that angle. It'll give us the cosine, which means to get theta, if we're actually trying to solve for the angle between those 2 vectors, what one more step do we need to do to solve for theta? The inverse cosine, yep. So we'll do cosine inverse of this value. And the way that cosine inverse works on our calculator is the way that our calculator is programmed, it only works with functions. So even though there are 2 points on the unit circle where cosine can equal radical 2 over 2, cosine's positive in quadrant 1 and quadrant 4, our calculator can't give both answers back. It only gives one answer back. So the way that cosine inverse is programmed on our calculator is that it only gives back a quadrant 1 answer or a quadrant 2 answer. It never gives you back an angle between 180 and 360, which would be quadrant 3 and quadrant 4. And the reason for that, if you look, you could think of these vectors as actually making 2 angles. There's always a smaller angle, and if we go around the other direction, there is a much larger angle. But this formula, the cosine theta formula, is always going to give the smaller one. If the v dot w over magnitude w comes out positive, we're going to get something between 0 and 90 because cosine's positive in quadrant 1. If it comes out negative, we're going to get something in between 90 and 180 because cosine's negative in quadrant 2. So it really always has 2 angles between them, but it's always going to give us the smaller one. So this is helpful in figuring out the relationship between 2 vectors, where they are in relation to one another. And even though I drew it in 2 dimensions, we could just as easily do this in 3 dimensions as well. And it wouldn't be any different. It just means when we do our dot product, there'll be a 3rd component. When we do those magnitudes, there will be a third value that we're squaring under the square root. So vectors in 3 dimensions have angles between them, just like vectors in 2 dimensions. And we're going to draw this one also just to kind of confirm the answer that we get makes sense. So vector v is negative 3, 4, and vector w is 1, 3. I'm going to draw those. So there's our v and our w. Just from the picture, what would you estimate the angle to be? 75? 63? Would you say, Eason? Less than 9, definitely less than 90. Pure facts. So we're looking for this angle right here. It is absolutely, definitely less than 90. We can see that from the picture. Where it is in relation to 45, it looks like it might be a little bit bigger than 45. Everybody's answers were bigger than 45. But we can get an exact answer for the size of that angle using that formula. Cosine of theta is going to be v dot w over magnitude of v, magnitude of w. So we need 3 values in here. We need the dot product in the top, and then we need each of our magnitudes in the bottom. So for dot product, when we multiply the x's, we get negative 3. When we multiply the y's, we get 12.
that -3 plus 12?
is -3 plus 12, yep. We've got our magnitudes in the bottom. If we were to, oh, I wish I could use my hand. Do just this calculation. V over magnitude of V. We've done that already. Do you know what the result is? Does anybody remember? It's a unit vector, right, in the direction of V. And then over here, we've got W over magnitude of W, which is the unit vector in the direction of W. Part of what this formula is telling me, and part of the calculation we're doing, is we're saying it really doesn't matter how long V and W are. That's not going to change the angle between them. Really, the only thing that matters are their directions. The direction for vector V, the direction for vector W. The length doesn't matter at all. So we could extend W out a lot farther, or we could extend V out a lot farther. That doesn't change the angle. The angle's still exactly the same. And remember, when we use a vector for only its direction, we typically use unit vectors. So that's why we're seeing these kind of two separate calculations here, V over magnitude V, W over magnitude W. Because the magnitude of these vectors has nothing to do with the angle. Absolutely nothing to do with it. And we don't want the magnitudes of those vectors to mess up our calculation. So the dot product will be very different if the magnitudes were different. But then by dividing by the magnitudes, it scales them back down to something less than 1. This calculation will be less than 1. So what do we get for magnitude of V? 5, right, because we've got -3 squared is 9, and 4 squared is 16, square root of 25 is 5. And then for the magnitude of W, square root 10, because we've got 1 squared is 1, and 3 squared is 9. So cosine of theta is 9 over 5 radical 10. Be really careful when you put this in your calculator, because we've got an operation in the denominator. So we've got to type this in as cosine inverse of 9 divided by parentheses 5 root 10. Our calculator, unless you use parentheses, is going to do things in order of operations. So if I just said 9 divided by 5 root 10, 5 root 10 is really 5 times root 10. Multiplication and division are going to be done from left to right. So it would really do 9 divided by 5, and then multiply that value by root 10, and we don't want it to do that. We need to make sure the root 10 is in the denominator. So we do need this separate set of parentheses around our denominator because there's an operation in there. And we're going to do this in degrees. I think degrees are a little bit more recognizable than those radian decimals.
I think on my math, they wanted to put the pi over.
Pi over a number.
Like pi over 2.
The angle is going to be pi over 2. Pi over 2 is 90 degrees. So the angle is going to be 90 degrees when, what's the cosine value at 90 degrees? It's 0. And the only way that fraction will come out 0 is if the top is 0. So for pi over 2, we can definitely do an exact radian value. For most of the other ones, though, it's going to be some crazy number that we're not going to be able to write it accurately that way. But if it ever comes out 0, then that means 90-degree angle, which means U and V are what with respect to each other? They form a 90-degree angle. They are perpendicular. They technically are well, no, because they can be moved into a different quadrant. If it was exactly 0 and 90, then yes. But they could be moved anywhere. So if the dot product comes out 0, that means the two vectors we're dealing with are perpendicular to one another. And that's going to be one of our geometric properties here in just a minute. What did you guys get for your angle?
55.
So we knew it was going to be less than 90, and based on the picture, everybody's guess sounded like it was more than 45. So it makes sense. Got about, yeah, 55.3. So it's always going to give us the smaller one. There is another angle between these two vectors, but it is a much larger angle, and the calculator won't give us that one back. It's going to always give us the smaller one. All right, you guys do this one real quick. And this one's going to be a lot harder to draw. You don't need to draw it because they're going to be three-dimensional vectors. But we want to find the angle between vector S, which is 3, 1, 5, and vector T, which is negative 2, 0, 9. So I want you guys to try that one. So in the top we do the dot product, in the bottom we've got the magnitudes. And the reason we're dividing by the magnitudes is because the length of the vector doesn't matter. That's not going to change the angle. What do we get for the dot product? 3 times negative 2 is negative 6. 1 times 0 is 0. 5 times 9 is 45. So you should get 39 for your dot product. And then in the denominator, we need our magnitudes. Magnitude of S is radical 35. Magnitude for T is 85. Since they're both under a square root, you could, and this will help you type it into the calculator easily, or easier, they really can come together under one square root. That way you're not having to type the extra set of parentheses because the operation in the bottom. So when I type this in the calculator, I'm going to say cosine inverse of 39 divided by square root 35 times 85. Dot product is positive. Magnitudes are always positive, and now our dot product is positive. So this cosine value is positive. So we should expect an answer less than 90 or bigger than 90? Less than 90. Cosine is positive in quadrant 1. If it was negative, it would be a quadrant 2 answer. So because this fraction is positive, when I do cosine inverse of a positive value, it's going to give us back a quadrant 1 answer, which is less than 90. So I know the angle between S and T is going to be less than 90 because the dot product's positive. Do we have an answer? 44-ish. If we just do one decimal, it's 44.4. Questions about angles? So far, yes. You want me to give you one that's not? So if your dot product comes out negative, then the value of that fraction will be negative, and cosine inverse of a negative would be between 90 and 180. So it all depends on the value of that dot product. Positive is going to be less than 90. Negative is going to be greater than 90. All right, so now we've got vector u is 2, negative 3, 1. Vector v is 5, 3, negative 1. What's the dot product? Dot product is 0. Because we have 10 minus 9 minus 1. Or 10 plus negative 9 plus negative 1. We've got a fraction with 0 in the numerator. I know that my magnitudes are not going to be 0. But 0 in the numerator means that the entire value for this fraction is going to be 0, no matter what the magnitudes are. You can still write them out if you want to, but just the dot product equals 0, I already know what the answer is going to be. Magnitude of u, I got square root 14. Magnitude of v, square root 35. But the value of that fraction is 0 because the top is 0. So cosine inverse of 0 is 90 degrees. This is one way that we can check to see if two vectors are perpendicular to each other, is by just quickly doing their dot product. If the dot product ends up 0, then our two vectors are perpendicular. And that's going to be one of our geometric properties here in just a minute.
This one is small, so it's not going with this one. Or I wanted you to give you power.
Oh, you know what I would do? I'd probably just do it in degrees first and then convert it. So if you did it in degrees, you'd get 45.
That's what I was saying. I think it was 3. There was like 2 or 3. Yeah, there's this one also. It's just those two.
Okay.
And I'll get the top one right and the bottom one right. I kind of had a guess on those.
Okay. Yeah, they're, you can look at your unit circle to help, but they are definitely at a 90-degree angle between one of each other. So 90 is the same as pi over 2. If you look at the next one,
It's low.
6, -6 slices exactly halfway through the quadrant, and then 3, 0 is on an axis. So the angle that goes exactly halfway through a quadrant is going to be 45. And you'll get 45 if you do the calculation as well. But then they want you to convert it to radians. All right. Thank you. In the homework, if you haven't finished your homework yet, Arturo has showed me that they do want the angles in radians, but they come out to be nice exact angles. Not any crazy decimals. So back in section 1 and section 2, we talked about how we can tell if two vectors are parallel. This is an easy way to decide if two vectors are perpendicular. So they're parallel if one is just a scalar multiple of the other. They're perpendicular if their dot product comes out to be 0. And we're going to have another way to check for parallel once we talk about cross products. I'm going to show you one more thing really, really fast, then we're going to go on break, because after break, this one thing before break is not real important. It's not something we use very often, but it's a term that you might see again. And it's finding direction cosines. So there are times in three-dimensional space where we don't necessarily want to represent a vector by components, which we can think of as either change in each of our coordinates or also as the endpoint if it's in standard position. There are some cases where we might want to know what angle that vector is making with each of our coordinate axes. So any vector in three-dimensional space is going to make an angle with the x-axis, it's going to make an angle with the y-axis, it's going to make an angle with the z-axis, and they might all be three completely different angles. So the direction cosines tell us the cosine for each of those values. And we could do cosine inverse if we wanted to know the actual angle. So this is helpful to represent a three-dimensional vector. By the angles it makes with each of our coordinate axes. Now I'm going to show you why this formula works for one of them, but then I'm not going to do it for the other two because it's going to look exactly the same. But if we had some vector in three-dimensional space, yes. We can describe that three-dimensional vector by its endpoint. We can also describe it by the angles that it's making with each of our coordinate planes. So we could say this vector is 80 degrees from the x-axis, and it's 20 degrees from the y-axis, and it's 50 degrees from the z-axis. The calculation is actually really easy, and it's something that we've already seen before. But if I wanted to find the angle that this makes with the x-axis, if you look back up at your formula up here, to find the angle between two vectors, you're going to dot them and then divide by their magnitudes. So we've already talked about just a kind of generic standard vector that represents the x-axis. Does anyone remember what it is? 100, which is I, yep. So we can think of the x-axis here as I, which is 100, and that would actually be a 1 unit vector in the x direction. But remember that the length of these vectors doesn't matter. That's not going to change the angle, which is why we divide by the magnitudes. So I really could take this vector, which has components v1, v2, v3, and to find the angle with the x-axis, I can dot it with the I vector. That would give me the angle between those two vectors. 100 is on the x-axis, and then v1, v2, v3 is the vector I'm interested in finding the angle for. So to find the angle between v and the x-axis, this angle has a special name, we call it alpha. We would do v dot I over magnitude v, magnitude I. This is our I vector over here. We've got components for it, so that makes it a little bit easier to see exactly what we're multiplying. What is v dotted with I? Remember, multiply corresponding components and add the results. Not v, v1. It's going to be v1 plus 0 plus 0, because we're going to do v1 times 1, v2 times 0, v3 times 0, and add them all together. All we get back is v1, the first component, which is the x component. So if I want the angle with the x-axis, I just end up using the x component in my numerator. Now in the bottom, go ahead. In the bottom, we want magnitude of v, but what's the magnitude of I? It's just 1. So multiplying them together is not going to change it. It's still just going to be magnitude of v in the bottom, because the magnitude of vector I is 1. So we've got v1 over magnitude of v. We've seen this somewhere before. If I wanted the angle with the y-axis, I could say it again? Yeah, that's the component for the unit vector. That's the component for the unit vector. If I wanted the angle with the y-axis, I could dot v with j, and I would just end up with v2 over magnitude v. If I wanted the angle with the z-axis, I could dot v with k, and I would just get v3 over magnitude v. Those are just the components of a unit vector in the direction of v. So we say that cosine of alpha is v1 over magnitude of v.
cosine of beta, so this is with the x-axis, is V2 over magnitude of V. This is our angle with the y-axis. And then cosine of gamma, no, that's not my gamma. Kind of looks like a y, is V3 over magnitude V. And that's our angle with the z-axis. And all those are the components from our unit vector. So there's two different things here. There are the direction cosines. Those are just the cosine values for the angles. Those are called direction cosines, when I just want to know the cosine value of the angle. And then we also have the actual direction angles themselves, which are the alpha, beta, and gamma. And to solve for them, we would just do cosine inverse. So there's two different things here. There's direction cosines, which is the cosine value. It's the components from our unit vector. But if we actually wanted to solve for the size of that angle, we would then do cosine inverse on it to solve for the alpha, beta, gamma. And these are just the exact same thing as our unit vector components. So it's just another way to describe the position of a vector in space. Instead of saying its endpoint from standard position or how the components are changing, how the coordinates are changing, you can describe it more as a direction, an angle with respect to each of the axes. So we're not really going to mess with that. There's really not a whole lot we're going to do with it. I think there is a homework problem asking you about direction cosines.
It was the first question, and I was asking for, I think it was 4i times, I can't remember, it was some,
Dotted with some other vector?
yeah,
Okay.
like 5j was it?
Okay. The easiest way to do those is to remember that I is 1, 0, 0, j is 0, 1, 0. And if you can actually see them written out as components, it's a lot easier to see what's going to get multiplied, what's going to get added. So I would write those, I would write anywhere you see I, j, k being used, I would write out what the actual components are for that vector. It'll make more sense. It'll be easier. All right, so we are going to have a break. It's 2:30 already. When we come back from break, we're going to talk about projections, which are extremely important. It's one of the most important things we can do with the dot product, in my opinion, is a projection. And we're going to see things with these projections come back almost every single chapter. So a projection, the way that I like to think of it and what makes most sense to me is we are taking a resultant vector, a vector that is the result of two other vectors being added together. So we're starting with the answer and we're breaking it apart into the two pieces that it started as. But just like any scalar number, if I said 8 is the answer, what's the addition question? What addition question will give you an answer of 8? A lot of them, right? Yeah. So it could be 0 plus 8, 1 plus 7, 2 plus 6, 9 plus negative 1. Yeah.
So there are an infinite number of answers for that question. So we can't just be given the answer. We also have to be given a little bit of information about one of the numbers or one of the vectors that we're going to be using. So what we're going to have is a vector that represents the answer, and then we're going to be given another vector that represents the direction we want part of our decomposition pointing in. And we're going to decompose a vector into two pieces. One of the pieces they're going to give us the direction for, and the other piece we could easily figure out. Because with these projections, the two vectors that we break them apart to are always going to be 90 degrees from one another.
This guy's so rich.
Good night. Mm-hmm.
$9 billion. They can pay that tax write-off too. I hope they're giving them money to do and stuff.
So we're going to be breaking a vector apart into two other vectors that are perpendicular to one another. So we might be told to take this vector and break it into two pieces, where one of the pieces is in the direction of V.
Is this supposed to be straight up and down?
Sure. However, what we're going to be calculating here is the projection of U onto V. Now, V might not necessarily be long enough to make U, or it might be too long to make U. We're only using V for its direction, which means somewhere in this formula, we're going to see V over magnitude of V. Because what is V over magnitude of V? A unit vector, right. Anytime we're interested in using a vector only for its direction, we shrink it down to a unit vector so that its magnitude doesn't mess up our calculation. So I want to use V's direction as one of the vectors to help me create the U. The U is the final answer. And we're going to decompose it. So U is equal to, we sometimes see it written as W sub 1 and W sub 2. And we're trying to figure out what W sub 1 and W sub 2 are. I know that W sub 1 is in the same direction as V. I just have to change how long V is, possibly. W sub 2 is always going to be perpendicular to V. So if I want U to be the sum of those two vectors, remember our parallelogram method back from section 1, if U is the answer to a vector addition problem, that means that U is going to be the diagonal of a parallelogram. And with projections, it's actually a little bit easier because they're always going to be rectangles, because W sub 1 and W sub 2 are always perpendicular to one another. When we made some of those other parallelograms, they weren't always necessarily rectangles. They had these weird slanted sides. But I want to make U be the diagonal of a rectangle. And V has got to be the direction for one of the sides. So I drew a box that has U as the rectangle and one of the sides following V. You notice that the side of that rectangle is longer than V. This rectangle that I drew, where V is, I'm using that direction, but I actually need something a little bit longer in order to have U as a diagonal. That entire side of the rectangle that's in the same direction as V, that's our W sub 1. That is the projection of U onto V. And then this other side that's perpendicular to that is our W sub 2. Now W sub 1 and W sub 2 add to be U from our parallelogram method. Says we can put both of those vectors in standard position and draw a parallelogram and U will be the diagonal. And then they gave us a little extra information. They told us what direction one of them needs to be in, the direction of V, and then the other one needs to be perpendicular. So we already know the direction we need it to be in. We just need to know how to scale it appropriately to be the correct length. Because right now, W sub 1 and V don't have the same length. W sub 1's a little bit longer, V's a little bit shorter, but they're always going to be in the same direction. So the formula for finding the projection, W sub 1 is the projection of U onto V. And the way that we calculate that is U dot V over magnitude of V squared times vector V. And we can actually rewrite this a second way. We could say this is U dot V over magnitude of V multiplied by V over magnitude of V.
So this is just going to be a scalar?
The U dot V over magnitude V is just a scalar. It's going to tell us how long.
Oh, times V.
So you can think of this two ways. The first way we have it gives me how I need to scale V as V sits right now. Now, what I did for the second way that I wrote it is I split apart my magnitude V squared. And I put 1 in each denominator. Because what is that right there? It's a unit vector, right? So that took V and it squished it down to 1 unit long. And then this value tells us how to stretch it back out so that it will make U appropriately. This is called the scalar projection. It's just how long is W sub 1. I know V over magnitude of V only has a length of 1. So whatever I multiply it by, which is this front set of parentheses, that's what the new length is going to be, U dot V over magnitude of V. So the scalar projection is just the length of W sub 1. And it's just this first part. If you want to know the entire projection as a vector, what the whole new vector is going to look like, we do this one. So this one is called the vector projection. Because the answer is a vector. The value in the parentheses is a scalar, and then we're multiplying it into vector V. So our answer would be a vector. So if I just gave you these two random formulas and just said scalar projection is U dot V over magnitude of V, vector projection is U dot V over magnitude V squared times V, we won't really see the relationship between them.
So the scalar projection is the length of W sub 1, which is our projection. And that's U dot V over magnitude of V. So they're two very related concepts. They're just asking a different question. The scalar projection is just asking us how long is it going to be. We already know the direction. It's in the direction of V. Scalar projection is just telling us how long the new vector is going to be. The vector projection actually gives us a vector answer. It incorporates the length that we found in the scalar projection with the vector in the V direction and puts them together to give us a full W sub 1 answer. So we're going to be given the U and we're going to be given the V, and we could use this formula to help us find the projection. There's also a vector projection orthogonal to V. Have we used the word orthogonal yet? Almost. Braces, orthodontist. Orthogonal just means perpendicular. This is the W sub 2. It's that second vector that we needed to create our parallelogram method and get U as the diagonal. Well, if we know U and we just calculated W sub 1, we said U was going to be the sum of W sub 1 and W sub 2. How can I solve for W sub 2? Just look at this formula right here. How do we solve for W sub 2? U minus W sub 1, because U is going to be given, and we use the vector projection formula to find W sub 1. We'll have two of those three pieces in that addition problem, and we could just subtract to find W sub 2. W sub 2 is just U minus W sub 1. So there's no fancy formula for finding the vector projection orthogonal to V. It's just finding the vector projection. That has a fancy formula. We'll be given the U, and then we can just subtract to find the W sub 2. Now, one of the good applications for this is with acceleration. I think I might have told you guys this already. Acceleration measures change in velocity. Well, velocity is a vector, so it has two components. It's got a magnitude and a direction. So if acceleration is measuring the change in velocity, we can break it apart into two pieces and actually pinpoint exactly how much of our acceleration is going towards changing our speed and how much of the acceleration is going towards changing our direction. Speed is always in the direction of motion. So if we know our acceleration vector and we know our direction of motion, we can take our acceleration vector and split it into those two pieces. And it will tell us part of our acceleration is going towards changing our speed, and then the orthogonal piece is how much acceleration is going towards changing our direction. So we use this when we break acceleration apart into its two pieces. And we can take an acceleration vector and decide if a particle is even changing direction. If we find that all of the acceleration is in the direction of motion and none is in the direction perpendicular to that, that means our particle is just moving in a straight line. It's not changing direction at all. It's just moving in a perfectly straight line. And we could figure that out with these calculations. So breaking acceleration apart is one of the main
applications that I know off the top of my head. Arturo, if you need to go ahead and go. I'm just going to do one example. But the video and the notes will be in Moodle.
Okay.
I'm just going to do this in 2 dimensions for now. Drawing it in 3 dimensions is a little bit trickier. And with the 2 dimensions, we can actually draw the picture and see how this all plays out on the graph. So we're going to find the projection of U, which is 5, 2, onto V, which is -2, 1. So U is being projected onto V. That means our answer is in the direction of V. V just might not be the correct length right now. So part of the calculations that we're going to be doing is figuring how we need to scale V appropriately, make it bigger or smaller, so that we can use it as part of the sum. So I'm going to draw these, show you what they look like, and try to make a guesstimate at what our answer is going to be.
So we don't just follow the formula?
Yes, you can follow the formula. So there's our U. There's our V. I picked a tricky one to start with. Probably shouldn't have done that. You want me to show you the tricky one or change the numbers?
Wait, this is tricky?
I mean, if you just follow the formula, the calculation's simple.
Oh, okay.
So I want to make a rectangle with the help of V that has U as the diagonal. That's what we're trying to do. The problem is the angle between them is bigger than 90. It looks like it is. If you look at the picture we drew up here, when I connect my U to my V, it connects perpendicular. You said go with it, Eason. But we're only using V for its direction, okay? So technically, we could extend this out farther if we needed to. We could also end up with a negative coefficient, which would make it go exactly 180 degrees. Anything along that line, we can think of as a scalar multiple of V. And I want to connect U to that vector or that line with a perpendicular line. So U is actually going to have to connect down here. So that's why I said this one was tricky, is because we don't actually connect it to V. We're actually connecting it to an extension of V in the opposite direction. So the piece that's in the same direction as V, that's our W sub 1. This vector right here that goes from the origin out to, it looks like about maybe 2, -1 or 2, -2. That's our W sub 1. And then the piece that's orthogonal to that, or perpendicular to that, is this one. That's our W sub 2. And it looks like that one goes to about maybe 3,3 or 3,4. And u is the diagonal of that rectangle, which means w sub 1 plus w sub 2 equals u, according to our parallelogram method. All right, so now we're going to actually follow the formula, see if we can figure out these values. So the scalar projection of u onto v, and at this point we've pretty much run out of symbols. We're going to do a lot of things where they just abbreviate it with the first few letters. So the scalar projection, the vector projection, divergence, a couple chapters from now. There's a bunch of different things where there's no more symbols left for us to use. They just start using the first few letters of the word. So the scalar projection of u onto v, this is how we need to scale v, or a unit vector in the direction of v. So this is u dot v over magnitude of v. Now I left off the v over magnitude v because that's just turning our v into a unit vector. And this says how to scale it. So u dot v over magnitude v is the scalar projection. It tells us how long w sub 1 is. And we're given a u and a v. What do we get for u dot v? -8. The fact that that thing came out negative is what tells me I actually have to go opposite direction of v. V is not pointing in the correct direction right now. Because when you do a negative scalar, it changes the direction 180 degrees. And then the magnitude of v is radical 5. So this is telling me how to take a vector in the same direction as v, a unit vector, and how to scale it appropriately so I can use it as one of the sides of the rectangle. So -8 over radical 5. Actually, I don't need to really. Huh? Say it louder.
You got it right, didn't you?
Yeah. Okay. For the projection of u onto v, we actually want to know the full representation of the w sub 1 vector. So we're going to do u dot v over the magnitude of v squared and multiply that scalar into v. And it's going to give us a vector answer. And that vector answer is going to be the w sub 1 vector. So I already know u dot v is -8. I know magnitude of v is radical 5. So squared is going to be -8/5. So we need to take v and multiply it by -8/5 if we want to use it to create u. So v was -2, 1, and we're going to multiply them by -8/5. So the scalar projection is the one that just comes out as a scalar, and the vector projection comes out as a vector. So my w sub 1 right here, so mine's not drawn to very good scale, I guess, should be 16/5 -8/5, which is 3.2 -1.6. So 3.2 -1.6 should actually be about there, I guess. So it never comes out perfect when we draw it by hand. And then if we want to know the piece that's orthogonal, we just do u minus w sub 1. Because w sub 1 plus w sub 2 is supposed to equal u. So here's my w sub 1. However way you want to write it. They're terminating decimals, so you could use decimals if you want. We're going to do u minus that. And our U was 5.2. So 5 minus 3.2 is 1.8. 2 minus negative 1.6 is going to be 3.6. So my W sub 2 should go to about 1.8, 3.6. So 1.8 would be about here. So it's pretty close. Not wonderful, but pretty close. Because we didn't actually use the original V. We didn't connect U to V. I actually had to extend V out with that dashed blue line and connect U to an extension that goes in the opposite direction of V.
So on the test, you gonna just draw that?
No, we can use it to help break apart an acceleration vector. And figure out how much acceleration is going towards changing our speed, how much is going towards changing our direction. So if the vector projection in the same direction as motion comes out to be 0, that means our particle is not accelerating at all. And all of the acceleration is perpendicular, which is going towards changing direction. So our particle would be moving at a constant speed, but it would also constantly be changing direction. So acceleration's got two components because it's a vector and we're able to break it apart. We could do this just as easily with three-dimensional vectors. None of those calculations is going to change. The U dot V over magnitude V, that just means there'd be a third component. And the projection, it just means we would have a third component in our answer for our vector. So on Thursday, today's Tuesday, right? Yeah, on Thursday, we're going to learn about cross product and we're going to have a vector project. Everybody looks at me then. A vector project.